I'm Bhavidhir V. Bharadwaj. Welcome to episode 54 of Genesis of Tomorrow. The following is going to be a conversation about quantum complexity, things of the sorts of phase transitions, anti concentration, and other such relatively under-cherished aspects of quantum science and technology with Dr. Abhinav Deshpande, an esteemed research scientist at IBM Quantum. Also, folks, if you're interested in such deep science and deep tech conversations and are able to derive even the slightest bit of value from the show, please support us by clicking the subscribe button so that we can keep improving the quality of the episodes and keep on bringing such wonderful guests over for you. And now, without any further ado, let's get right into it. Enjoy and thank you. How someone who goes from IIT, then Maryland, then Caltech, this entirely academic setup of learning and excavating their interest in a particular subject such as physics and quantum physics, when they then transition towards industry, getting to work with maybe developing implementable solutions which may in future become products or services, or maybe just tangible stuff that can be implied and applied to reality, that translation often happens through the means of computation. There's quantum
hmm
theory, quantum physics, and then you want to make it applicable. We generally right now do that through the means of computation. How does that evolution for a kid, a young individual who does their undergrad, maybe masters or directly PhD, then they move on to industry, that okay, I do not want to go into academia, I want to get into industry. Suddenly the atmosphere changes from merely doing research for the sake of research towards doing research with a specific emphasis on an applied output per se. How
hmm
does that work for a young individual?
hmm Yeah. Okay. Yeah. Thanks for that question. Maybe I don't know if I can give a general answer, but I
Mm,
can just share how the evolution looked like for me.
mm,
Um, I think okay. So at the beginning of my graduate school research, I was very much interested in what computation can say about physics, in the
mm,
sense that understanding um, problems from the lens of computational complexity theory. And I, at the time, thought these were really powerful tools that can implicitly say something about physics, even though on the surface they don't seem very much like physical statements. I had just then discovered this fact that, in effect, computational science is also a statement about what is possible or not possible, according to our laws of nature. So it's not divorced from physics in that way.
mm,
Yeah, so I was at the beginning of grad school, I was of this opinion that, maybe you don't actually have to build a quantum computer in order for it to be interesting.
mm,
Um, that quantum computing and its implications on physics are already rich enough and interesting enough that these capitalist minded people, we don't have to satisfy them in order to just have fun as physicists. But I think along the way, I guess got this feeling that yes, it might be cool to actually build a quantum computer and do fun things with it. Mm.
mm. You.
Yeah, part of this evolution was also spending time at Caltech. I
Mm,
was still in my grad school when I spent a summer in 2019 at Caltech, and the group would have um, lunch every day for an hour or so, and I got to spend time with Dr. John Preskill there, and he was of this opinion that, he sees the point that quantum computing is already interesting physically, but it would be really cool to build a quantum computers too. And his excitement was infectious, I think. Also, in my PhD research, I collaborated with experimentalists,
Hmm.
and I was at Maryland in the Joint Quantum Institute, where there's many experimentalists who are actually doing like all these really cool research, and being around people who are building things and trying to make it happen um, makes you want their efforts to succeed.
Hmm. Hmm. You've also worked with people of the likes of Alexei Gorshkov and Bill Pfefferman who got these very fundamental, I mean, testaments in regard to vouching for quantum supremacy. And before we move on to the more theoretical or maybe technical explorations or expedition, it would be fundamental if you could explain to maybe the uninformed of why a quantum computer is more in any way or sense than just maybe if one had to use a significantly faster or more efficient classical computer.
Yeah. So right now, I think quantum computing is promising because it computes differently. Um, it's hard to say. It's hard to use a particular adjective like faster or more or better. It's just different, and um, because it also, theoretically, any classical algorithm can also be written as a quantum algorithm. In that sense, it's also a larger set of problems than classical computers. Um, so, in like this very theoretical sense, it is more. Um, but in this practical sense of, I mean, you probably don't want to be playing like regular minesweeper or something on a quantum computer, right? If that day ever comes to fruition, you probably want to use quantum computing for some problem that a regular computer cannot do. And yeah, the quest is on to find what problems there are that fit best on quantum computers.
In that regard, then maybe to extend that a little bit, the claims about quantum advantage right now, how well based in actuality are they? Claims that are actually based on actuality and then ones that maybe are a little blown out of proportion. Like, what actually is the quantum advantage right now?
Yeah, quantum advantage now is understood as this term where we have convincing evidence that a quantum computer can solve a problem that we believe um, would take a long time on a classical computer. So there's very like many aspects to what quantum advantage is. So one is this theoretical sense where we call advantage as something where when you make the problem size larger and larger, the time taken by a quantum computer, say, scales polynomially in the size of the problem, but classically, you might take exponential time or longer. So there are some problems like simulation of time dynamics, quantum dynamics in nature, being the most relevant one, where we have good reasons to believe there's this theoretical quantum advantage in this sense. And then there's other problems that are constructed, that are handcrafted, where so as to that give good evidence for quantum advantage. But one problem with some of these, like random circuit sampling, is that it is not easily verifiable. So you have a computation in which is basically sample from a random quantum circuit. The and it's a very well defined problem. Um, but it is hard to verify that a quantum computer that is solving this problem is actually working correctly. And because right now it is quite hard to build completely noiseless quantum computers, this is a practical problem.
In that regard as well, you've got some significant work on the Gaussian boson sampling, which again is a very significant way in which right now we are able to prove or attest to the quantum advantage. What can you say of maybe a comparative analysis between the hardness of sampling or as compared to the hardness of just calculating a specific value?
Yeah, so I was coming to, so I had mentioned one facet of what advantages. The other facet is that we have these experiments, and experiments are always done at particular finite system sizes. So an experiment can, in principle, to a pedantic mathematical minded person or a computer scientist, an experiment can never witness some asymptotic claim, which is what advantage is about. But practically, I think that may be too pedantic an opinion. It is perfectly valid to ask, like, if I have some 60 qubit device, how long will it take to, solve a particular problem? Yeah, and coming to this question, there are differences between sampling and then calculating a number, like expectation values. The latter is somewhat more verifiable, but theoretical computer science, uh, yeah, like we don't have as good a tool in theoretical computer science to be able to prove that some there are these problems which on average will have like a classical speed up. Sorry, we don't have as good a tool in theoretical computer science to show that computing expectation values is really hard on classical computers.
But we have a grasp, not a tool, but we have sort of this intuitive grasp that that is the case.
Yeah, we believe these are hard on classical computers, but easy for quantum computers. But we don't have a proof. I mean, in many parts of theoretical computer science, in complexity theory, ultimately a so-called Hardness result basically just um, is the same as saying that lots of smart people have thought about it and they couldn't come up with an algorithm, and that's why we believe it's hard.
Your work then in these phase transitions, complexity phase transitions, also vouches for how maybe the addition of physical parameters, now that can be noise or something else in that regard, that can make a system just transition from being easy to simulate to this hard, become hard to prove. Could you walk us through this complexity phase diagram of
Uh-huh.
and at what point does a physics related problem starts to become a computational constraint when we are not able to prove it to be hard?
Mm. Okay, yeah. So the idea behind the work is follows. Let's say I have some lattice where at each side of the lattice there can be a boson, or many bosons or not. So you can just think of an optical lattice. These people make these traps, and at certain locations you can have atoms sitting there, bosonic atoms sitting there, which can hop from one site to another, this neighboring sites, let's say. And now, so let's say you have a lattice where most of the sites are empty, and there are some sites occupied by bosonic atoms, and you let this evolve in time under some time dynamics, which we write as a Hamiltonian, that describes just bosons hopping from one site to another. You could add long range hopping, but that doesn't matter. Um, and now, so initially, this system is very easy to describe classically. It's just atoms sitting here and there. And so initially, if I want to solve the problem of sample from the output distribution after time evolution and measurement of boson positions, that is easy. Now, after some time scale that we call the complexity time scale, which is essentially the time it takes for bosons to start seeing one another, this problem of sampling from the output distribution becomes hard. And it is very curious that uh, for some regimes we have a very tight characterization. At most timescales, it's we either know it's easy or it's hard. There's like not an in between. So that's why we call this a complexity phase transition.
Hmm. Again, maybe a little bit on the this provably hard side of things. Um,
Hmm.
with things, especially of the likes of simulation, when you try to simulate processes or physical phenomena, so on and so forth, you often
Simulate what? Sorry.
simulate anything, physical processes or physics related phenomena in drug discovery, or maybe some permutation combinations of certain different categories or something, anything. There comes a distinction of how some things are relatively harder to simulate than others.
Hmm.
What is the difference between we just have not found yet a good enough way to do that and something being provably hard? How, as a
Mm.
researcher, do you distinguish that?
Wow, yeah, that's a great question. I love that question a lot. Uh, so I think it is more of um, what the theoretical computer science community has arrived on is like a procedure like that goes like this. I mean, you ask whether it belongs, after some transformations, whether it is a problem that you have seen before or that somebody else in the community has analyzed before. And if so, um, then if these transformations are easy, then you know that this particular problem is in the same complexity class as some other problem. And while it may be hard to be able to ultimately say how hard a particular problem is, um, at least through this technique, what we can delineate is these different classes of problems that we know in for each class, two problems are roughly of the same hardness. But strictly speaking, this exercise hasn't mathematically proven anything about whether one problem is harder than another. Um, but for that, we have empirical evidence in that.
Mm.
Lots of people try to look for efficient algorithms for like a wide variety of problems. I think NP is the most famous such class, right? Um, if P equals NP, the world as we know would be very different. And it would, first of all, it would give you $1 million because it's one of the like great unsolved problems from the Clay Mathematical Institute. but it also means a lot of fundamental things. Um, so lots of people have tried and are still trying to look for efficient algorithms for NP complete problems, but haven't been successful. So we take that as evidence that maybe P is not equal to NP, and that maybe there don't exist efficient classical algorithms for any NP complete problems. So we build up evidence like this, and I use evidence in the sense of, in this Bayesian sense, in that someone tries to work on something and doesn't find anything, right? There is not a proof that there's nothing out there, but it is evidence in the sense that it makes you update your prior belief that there is nothing out there.
Yeah, it sort of becomes this iterative hypothesis testing kind of a procedure that you keep on doing continuously, if I'm able to quote that right. Because
I suppose autonomously, maybe we are doing something like that.
because there are a lot of because okay, coming to this facet of noise, let's say how fundamentally it's categorized or intuitively you assume it to be the enemy for quantum systems. But your work itself and even other particular in general advancements in the understanding of open quantum systems and how noise and energy dissipation they work, innumerable times this aspect of noise does not particularly hinder the efficiency, but our ability to harness it is rather able to make the quantum system more efficient per se. Question primarily: do you think noise is a feature or a bug? That is a nuanced answer, I think, rather than just a yes or no. But how so? Since you
Hmm.
formally studied it.
Yeah. Okay. So I would say noise is mostly a bug, um, because if you could understand enough of it and be able to control and harness it, then I wouldn't call it noise. So in some sense, it's tautological because noise is inherently the part of your system that you cannot control. Mm. And the more you learn of your system and the more you're able to control things, I guess the more knobs you have, it's always better. Yeah.
But okay, I got to know this maybe a little while back itself, rather recently. But there was this study done by Penny Lane or maybe some other organization. What they found out in that was they took different quantum machine learning algorithms and
Mm.
their uh, evaluative data, how they performed on different evaluation metrics, so on and so forth. And one sort of, again, this is a very heuristical, reminiscent view that I have of that study. But what they found out was essentially that most of the quantum advantage that came from those quantum algorithms that they analyzed was not in turn due to entanglement, but rather the presence of ways to effectively handle noise. And when they removed entanglement per se from those algorithms entirely and made them, in essence, classical, then the performances rather increased in terms of efficiency and effectability.
Mm.
So the sort of question that I was deeming to ask from you is: noise is a hindrance, a sort of pain when you're trying to fathom or build quantum systems. That's one thing. But maybe it's coming from my novice nature, but how do you look at it? Because considering it completely or entirely a bug becomes maybe a little counterintuitive when there is a little bit data, quality data, that says that the advantage from quantum is maybe rooted into the ability to fester noise structurally.
Okay, I'm not sure of this particular work you're talking about. Um, but yeah, maybe to
Maybe,
qualify
yeah,
what I said.
tell me from your study, your background,
Yeah,
how do you look at it?
right. So coming to, I think, open quantum systems, it is true that we don't want a quantum computer to be completely closed, because then we would not be able to even interact with it,
Hmm.
or essentially read out the answer. So there are some forms of dissipation that are really important, and we want these to be present. Um, I think when building qubits, for example, this is one fundamental source of experimental hardness, right? You want to isolate qubits enough from the environment, but you also want to be able to measure the qubit when you want it to. And so, in a sense, you don't want the environment measuring the qubit. You want you, the human,
Yeah.
to be the
Yeah.
one measuring the qubit. Um, so yeah, forms of dissipation are helpful, and some of my research is also, like recently, I've been interested in what forms of dissipative dynamics are have quantumness in some sense, because some forms of dissipative dynamics are not they don't render a system entirely classically simulable. And yeah, there are some advantages to having dissipative dynamics. But yeah, I think maybe the terminology I used for my previous answer was that noise is whatever you cannot control in that
Yes.
sense.
Yes. No, I get that. In that regard, maybe a little bit about this, the dissipative advantages that you were talking about. What exactly have you been trying to study in that regard, and what are the distinctions that you are able to infer from that work?
Okay, yeah. So um, in, say, one work of mine with other collaborators, we looked at, say, fermionic systems, and we asked, okay, what kinds of dissipative dynamics. So we are talking about free fermions, so just fermions that again do nothing but hop from one side to another. These systems are efficiently simulatable on a classical computer, despite the bosonic equivalent of this not being easy to simulate. Um, and actually, if you're interested, there's a very cool link between, like, this duality between bosons and fermions in physics, and the permanent and the determinant in computer science. In fact, there's a whole line of complexity theory where people try to show that permanents are much harder to compute than determinants. I mean, we already believe that we permanents are sharply hard, but there's a line of work called geometric complexity theory, where they actually try to prove, like, lower bounds on these things. But yeah, anyway, so in this work we are looking at free fermions, and we add some dissipation, and we just analyzed how hard is it to simulate this dissipative dynamics of free fermions. And yeah, it turns out that you can add certain forms of dissipation that effectively make the system hard to simulate on a classical computer.
And how?
And
Yeah.
one way we did that was just by proving that um, you, with certain forms of dissipation, you can have you can actually affect gates between fermions, and then you have a universal quantum computer.
How hard is it to categorically and structurally induce dissipativeness, as in how you want to from a hardware perspective? I actually build that mechanism.
Oh, I would be the wrong person to ask that. Yeah, I don't know. Mm. It depends a lot on the system. I
Hmm.
mean, when people are working with, say, atomic systems, one way of inducing dissipation is you couple the you couple the atom to some light. Say, you try to activate certain transitions. Um,
But it is a relatively sort of, is it an inconvenience? Like maybe just theoretically again, just trying to know, is there inconvenience attached to incorporating this dissipative dynamic into our system, firstly, and secondly, is that inconvenience greater or lesser than the advantage that inducing dissipative dynamics to our system facilitates us with? So
mm.
sort of a return on investment.
Yeah, I would say maybe, yeah, you probably don't want to go great lengths to modify your system to make it more dissipative. The way I would look at it is that if you have characterized your system and you understand that there's a particular form of dissipation that's already there, maybe you want to try and understand how you can still use it. um, but yeah, but I wouldn't go so far as to deliberately go and try and um, effectively heat up your atoms
Oh.
or system
Hmm,
to
hmm,
it.
hmm.
Yeah, that would be counterproductive, I think.
That makes sense.
Yeah. Okay. So I was speaking about how some of my work has looked at dissipative dynamics and hardness of simulation, and like the utility in other forms. So I mentioned one. Yeah, there was another where we looked at certain forms of measurement induced dynamics. The idea is that you have a quantum system and you do various forms of this dynamics where, say, you measure a qubit and future operations on the rest of the system depend on what the measurement result was. So this is adaptive dynamics. And yeah, there's great power in having this sort of adaptive operations. Yeah.
Another one of your personally more interesting works that I found was in the transition of anti-concentration.
Hmm.
Now, that as a concept is just about how the states need to be spread out for their probability to, for the classical computers to not be able to guess the peaks of the probability distribution of the quantum states. But trying to explain the advantage that anti-concentration facilitates in quantum computation to the uninformed or somebody who does not have idea of what anti-concentration does for quantum systems.
Hmm.
Firstly, how does that happen, and secondly, if a quantum system concentrates its entire probability, does that then in essence make it more translatory towards a classical system or not?
I didn't catch the last sentence.
if if
If what?
if a quantum system, it concentrates its probability, like going against anti-concentration, it concentrates its probability, right? You measure it and maybe it just drops down to one particular
Hmm.
thing.
Hmm.
No, maybe not measurement, but like it concentrates probability distribution to, let's say,
Yeah, yeah,
one minimum or maximum, whatever.
right.
Does it become classical in its essence, more closer to a classical essence, if even if it's still quantum in its hardware, but how we interpret it, does that start resembling how we interpret classical inferences?
Yeah, I see the question. Okay. Wait, what was the first part was okay,
Just
just an
explaining
explanation
anti, yeah.
of what anti-concentration is. Yeah. Okay, so in the quantum specific uh, case of what we are talking about, anti-concentration was first introduced as an idea. Uh, okay, let's step back a bit and see what the goal was. The goal was to try and show that simulating boson sampling on a classical computer is hard for a complexity class, and in the senses that it's classically hard. And what people were trying to do was show a contradiction, right? Basically, you set it up such that if you have a classical computer that can do exactly what the quantum computer can do, which is sample from the probability distribution, um, say the ideal probability distribution, up to some additive error, then then you have a reduction
Mm.
that's to another problem that we also believe is hard for a classical computer. And in trying to show this reduction, this is an argument that you don't carry out in real life, but it's like a hypothetical argument, which is that you end up talking about how hard it is to compute output probabilities. And now, what anti-concentration is saying is essentially that if I pick a random outcome, the output probability of that is not you know is not so small that I can basically just guess that it's zero and get away with it.
Mm.
Okay. Yeah, so effectively what we want to do is be able to say that computing a random output probability of a random outcome of a quantum circuit is hard to estimate. And now it would be a problem if quantum circuits are, they have large probability mass on some outcomes and close to zero probability mass on other outcomes, which would make the probability of a random outcome be very close to zero. So we don't want that to happen.
Mm.
And that is exactly what anti-concentration is saying, which is that, you don't have such large concentration of probability mass on small outcomes, on like small locations. It's more spread out. That's why the term.
Mm.
Yeah. So anti-concentration gives us some degree of belief in this statement that approximating random output probabilities is very hard. Now, that is not approximating random output probabilities is not what a quantum computer does in real life, but it just is somehow magically the case that it suffices to talk about the hardness of this problem. Okay. Yeah, coming to the second question, which is whether having a probability distribution that is more concentrated, does that make it classical? And yeah, no, the answer is no, because let's say I took Schur's factoring algorithm. In the cases where it's useful, we believe that the probability of getting the right answer, of finding some order that is informative, is actually quite large. It's like 40% or so. So yeah, there are cases where um, the you know the output of a quantum circuit can be peaked in this sense. It can have large probability mass on some outcomes, but that doesn't mean it's easy to simulate because we cannot predict in advance where that peak will be.
One thing that struck me while you were explaining that, coming back to the idea of noise a bit, in
Hmm.
areas such as cryptography or
Hmm.
security based applications, and how now there are this entire field of post quantum cryptography or quantum cryptography per se, and then you talk about AI systems, autonomous AI, where a system, a computer sort of, a computation will have enough autonomy, a variable degree of autonomy, to exist through reality.
Hmm.
In that regard, if, let's say, the idea of noise, since we categorized it as a bug primarily due to its property of being, of introducing unnecessary randomness to our equation, our system, maybe in a use case such as cryptography or security for these black box systems of an autonomous AI, let's say, does the addition or attribution of noise or quantum noise per se, noise in quantum system, that's what I mean by quantum noise, does that
Hmm.
serves maybe as a feature to the overarching use case? It may be a deficiency for the quantum system, but its utilization in that classical context of securing something like an autonomous AI system, does that serve as a feature, maybe become a feature for the overarching use case?
Uh, yeah, I don't understand the connection between these things all that well, like autonomous robots and cryptography and noise. Yeah, yeah. From the point of view of where I come from,
Hmm.
um, yeah, I don't really know.
In that regard, okay, I'll maybe set out a tangential context to that.
Hmm.
Um, if we can prove that a system is provably hard to simulate,
Hmm.
yes, does that mean that it is also provably hard to reverse engineer from? That can be said, a correlation that can be drawn, right?
Mm,
Because where
yeah,
I'm okay,
interesting point. Um,
because if that be the case, then the complexity and the property of any process being provably hard, it can be utilized for designing these AI systems. And why I'm bringing up AI suddenly, I'll explain that as well. You can use this provable hardness, this regime of hardness, to prevent any sort of security collapse. Why now autonomous AI? Why I'm bringing that up?
hang on.
Yes.
Security collapse in the sense of like what does the attacker have access to, or what are they trying to
Yes,
do?
it can be the access flow, or it may be something like adversarial cloning as well. So, like you get into the system, you see the data, and then you clone it.
Hmm.
So, those two things. Let's take those two connotations when we use security collapse. Why particularly autonomous AI? Because with traditional systems, may it be the internet, may it be accounts, may it be encryption mechanisms, so on and so forth, or normal rule-based AI systems, there is the level of autonomy is not there, or it is very low in terms of what the system is doing. It is being allowed to do something. When you talk about autonomous AI, or when Demis Hessabis from DeepMind talks about autonomous AI in maybe medical application, healthcare application, or Palantir CEO Alex Karp talks about implication of superintelligence and autonomous AI in military and defense applications, the core property is you do not get to have a particular say. You tell that model, that agent, what to do, how it does that. Maybe you provide some parameters here and there, maybe some constraints.
Okay.
But after that, there is not any intervention in which, or any way in which you are able to even intervene in how it goes through accomplishing that task.
Hmm.
And that variable degree of autonomy, complete autonomy, is what raises a question about how then do you secure it when you're not able to intervene, when you are not able to observe the internal working. How do you secure that black box? Because for
Mm.
security, you need opacity, but for governance you need transparency.
Mm.
So in that case, I'm just, again, this was a very I'm sorry if that became a very random thought trail, sporadic thought trail. But when you need transparency for governance and you need opacity for security, how about you use quantum quantum's better ability to generate randomness to facilitate that?
Yeah, I think there's possibly really nice questions uh, relating to these things in especially quantum cryptography and um, yeah, questions like I don't know how you prove to someone a certain fact without revealing anything other than the fact that you know
Hmm.
it
Hmm.
you
Hmm.
know
Hmm.
like zero knowledge proofs. And,
Hmm.
let's say you want to give a website, you know, you just want to prove to the website that you know your password and you indeed are this person, um, and maybe actually sending the password is risky, or yeah. uh, and I haven't thought so much about AI or autonomous AI for that matter. But yeah, I think there are really nice questions here. I do go to some quantum crypto talks, um, and for a long time I used to be somewhat confused about like the different notions of uh, like different security schemes and so on, and I still do, but I find them uh, nice to think about nevertheless.
Hmm. Marching into a very important segue, in my opinion,
Hmm.
for other young folks, maybe a student in their early years of undergrad, a master's student, or maybe a young PhD researcher. What, in your opinion, are the more important facets or aspects that they must optimize for in these years to carve out a, not only a successful career per se in a traditional sense, but also be able to, okay, how do you articulate it, be able to carve out better discovery or exploration in whatever it is that they are doing,
Yeah,
because research is all about that exploration and valuable output per se. How do you optimize for that as a young person?
yeah. This is again a lovely question. Um, I think what you want to do as a young person, say in college or after or before, is yeah, try and identify the things that make you go wow. I mean, make you go, oh, I wish it would have been me who discovered it. Okay, like being young, I mean, your age is, I guess, yeah, like you feel like you are late to the party, right? But it, I think, is still a matter of great intellectual joy in rediscovering something, or um, discovering something on your own, and then finding out someone else did it, maybe 40, 50 years ago. uh, I think that should not be deflating, because in a way, now you can see how someone at that point in time felt when the first person to come up with something may have felt. Um, and I think one should try to find these little moments of joy uh, when they understand something, or create something. And yeah, I think try to identify um, what brings you joy. I think that's the great quest. And yeah, when you're young, you have, I think it's really okay to just go out there, be maximally explorative. You never know when you might like something that something you think is way out of your field today. Um, yeah, I think I myself um, have learned things from disparate fields that I probably wouldn't have thought before that might be interested in someday. And I think one should also have this work ethic of trying to, you can have fun and all that, but next day you want to be back at your desk and trying to
Right.
make things happen. Um, yeah.
Extension to that, an extension to that. After these years in a setting of an academic setting, when you transition into industry, the as we were discussing earlier as well, the definition or the expectations of what a research must incur, they seem to change a little bit. Where maybe in your undergrad years or your master's years, it was about working at a lab, uh, in getting involved into the research work, getting involved into meaningfully able to contribute towards a paper and build up to that paper. Suddenly, when you're
Mhm.
working in the industry for a company, it becomes a little bit less about only and solely focusing upon that, oh, I want to get a paper out, but also about how that paper or that research output ties into the greater picture of the organization's or the industry's success.
Yeah.
How do someone who's early out of their school, they better acclimatize to the industry expectations, and what all must they prepare themselves better for, to
Mm.
better succeed in that environment?
Yeah. I think it's definitely the case that maybe as academics sometimes we focus on too narrow a problem, and you know yeah, maybe, okay, say a few hundred people cite you or something in the next few years, but that's like not the end goal. You do want your work to be used by people, and you want it to actually make an impact. And I think having this, like, as even in academia, as you progress in your career, I think um, your taste improves. So you get better at picking problems that have both a good likelihood of actually of you having some impact on, and also the problem itself, if it's solved, being useful to other people. So I think that's something that just comes with time. But being able to work in teams is really important, because um, I think the problems that are meaningful and to be solved, they are pretty big for one team, one person, or a handful of people to solve, right? Um, I think industry is really good at um, effectively getting many people to collaborate on the same problem, um, and I think one has to be comfortable with contributing in a team. Um, it's small bits here and there, but it's like you are a sculptor uh, working on some really large statue, and you see a tiny bit, but once you step out, collaboratively, you have built something grand.
Dr. Abhinav Deshpande, the final segment of the show, what would be your word to humanity at large?
My what? My
Your word, your address, your message for humanity at large?
um yeah, I don't want to be able to, yeah, I don't think uh I'm qualified enough to say something to humanity at large, but if I have a message, or if I have something to share about the kind of ideal I want to strive towards, it is to be, first of all, a better human being to everyone. And I just want to positively impact people I interact with, and through my work, leave a positive impact on, you know, just both physics and then industry, and through our quest of building a quantum computer society at large. And I guess this is a bit more personal, but yeah, I say through my progeny, I hope to leave better people in the world too. Yeah.
Thank you so very much for this entire conversation. People will be able to not only take away the technical nuances of the different facets that we discussed about quantum technology, quantum computing, science in general, but even such anecdotal advices that they may be able to benefit from and through whatever they are going through. So thank you sincerely and dearly for having this entire conversation. Thank you so much.
Yeah. Thank you, Bhavya. That was fun.
Okay.